So my idea, I think I had mentioned this before. What I wanted to do was basically to finish like the material today, and then the next two remaining classes, I would do like more like examples. You could call a review session, but it would be more like examples or things like that. Before our final exam on Wednesday, which is 1 week from today. So I'll try to also send you like, I mean, once I have finished today the class, I'll have like I will know exactly what we finished covering. So I'll send you like a study guide for the final, uh, either today or sometime tomorrow, um, tomorrow in the morning. So, but yeah, like there's not like I was going over like the book, like the topics in the book. And except for the law of large numbers, which was my plan to do today, and the convolution, which I still haven't told you what that is, and that's an interesting idea. There were not that many other topics left that were like, too like important to go over. So yeah, that's kind of my plan for wrapping things up. Like when it comes to the course material. Okay, so yeah, last time probably was a little bit too technical in relative to many of the other classes we've had, but it was just because we were discussing the central limit theorem, but like it's maybe more important just to remind everyone what the central limit theorem said. It was basically that if you have where did I copy this? Let's see, let's see. I think I copied the statement little bit earlier. Yeah, right. So if you like the idea of the central limit theorem was like, well, you have a bunch of random variables which are independent, and you should think of each of these individual random variables as like the outcomes of a possible experiment. It's just that you're kind of like this same, you're kind of repeating the experiment over and over. So the experiment could again be throwing a coin or throwing a die. So that's just, like that's an experiment that you are repeating under the same conditions or whatever it takes, so that like the probabilities on a given experiment to obtain the certain outcomes are the same. So if that happens and you add up these random variables, okay, after you have like so you add up the random variables, and then you kind of have to you kind of have to recenter it. So shift it again so that the sum has like this like shifted sum has like average zero. And so after you like kind of shift the distribution so that it has average zero and rescale it appropriately so that the variance remains fixed at the value 1, that after once you let n go to infinity, will be getting closer and closer to the standard like Gaussian of mean 0 and variance 1, in the sense that where did I write this? I think I wrote this a little bit earlier. In the sense that the probability for this rescaled sum to be between A and B can be computed using the normal distribution or the Gaussian integral. So again, I'll try to do some examples next time about this. In practice, how this is used is that you wanted to compute a probability, and if it's relatively plausible that you are under the conditions of the central limit theorem, then you would compute your probability by just like computing this integral. Of course, in practice, like you don't compute the probabilities taking a limit with n equals infinity, you kind of say, well, when n is large enough, you would expect that this actual probability to not be too different from this one. So you kind of like, just like, end up doing like, end up computing this value, whatever it ends up being. So it's not that in like, if you want to use this in applications, it's not that you would work with the exact equality. Rather, you kind of do like an approximation, and you say, well, this probability, um, once n is large, roughly approximates this probability. So again, use like I'll do some examples next time, so that you can see in practice how this works. But that's more or less like the philosophy of the central limit theorem. Again, like this is, if you open like these books, like in like biology or like um, electrical engineering or anywhere where like some sort of statistical methods are used, uh, well, boosting statistics obviously like will kind of justify the appear like approximating many things with the central limit theorem, with a bell curve or like a Gaussian distribution because of this central limit theorem. Although in practice, like it is a little bit more tricky than that because you know making sure that you would have like the hypotheses that are required, that is not so straightforward. But I mean, if you want to make a rough guess, it is like a good starting point, and then you can see how much things differ from like the actual uh, probability and actual results. But yeah, I'll do some examples about this on Friday so that you see how it works. Like the problems, I mean, are relatively straightforward because the only thing I don't like about these problems is that obviously you cannot compute this integral unless like you put here negative infinity and infinity as a bounds. So in practice, you need like some sort of table. So there are like all these tables. If you open a look on probability, there are tables that give you like approximate values more or less for this thing, or like from the table you can kind of guess like what this is supposed to be. So it kind of becomes a lot of like a problem about it feels like very oh, let's just plug in this into the table to see what we get. So it's not something I want to emphasize too much because there's not much like conceptually going on, but it's still kind of useful to kind of see it like a couple of times so that you see how it's implemented. But yeah, it just boils down to there's like this standard table for the probabilities of the for like the values that this integral takes, and then you just compare like the quantity that you are interested in with those probabilities in this integral. Of course, like now you can just use Wolfram alpha, or I'm sure like a calculator would also work to just approximate that integral. But I'm just saying it is literally just like an approximation problem of plugging in some numbers in the calculator or Wolfram alpha. But I still would do some examples so that you get like an idea of how this is used in practice. So for today, like the two main topics that I wanted to discuss were like this law of large numbers and the convolution formula. But both are interesting, and the law of large like either either of them is a lot more digestible than the central limit theorem. So let's talk first about the law of large numbers. It usually comes in two versions. I'll do the one that's really easy to explain is what's called the weak version. The strong version, like it kind of requires a detour that is not worth going into. But there is like something that's called like a strong version. But it is a little bit more confusing to wrap your head around, especially for a course that doesn't rely very a lot of analysis or very so. I'll just stick with this one. This is like what is usually in most textbooks, like the one that we have, like the official textbook for our book. So basically, it is a similar setup of the conditions in the central limit theorem. So you have like a bunch of random variables. So you have x1, x2, x3, up to xn. So these are going to be independent random variables. Uh, and the idea is that again, you kind of have to think of these as like copies of like the same experimental setup. So you have to assume that you know the probabilities that like the random variable takes a specific value is independent of like which random variable you chose. So in the discrete case, um, you can write this as saying that the probability that x1 equals like a value x is the same as the probability that x2 equals a value x, which is the same as the probability that xn equals x. So they all have the same probability of taking a particular value. Um, and in the continuous case, you just say that in terms of the density function. So you are assuming that the density functions, like as a function, they are the same. You would say that fx of one fx2 of x, blah 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 blah, f of xn of x. So like what this statement, regardless of how you write it, what this statement is saying that each random variable takes the same values with the same probability. So the random variables. And so what happens now? And this is kind of like the nice thing about the like the law of larger numbers is that that's kind of like a connection with like statistics. So for like what you could do is like imagine you wanted to imagine it's supposed that you like take a average of this. Imagine that you add up these random variables, right? So imagine that you do x1 plus x2 plus xn, and you divide by n, right? So that would be like some sort of average, right? So you can think of this as some sort of like very naive average, right? Sometimes it is also called the sample average. Okay, but so it's kind of like averaging out like the values that the random variables could possibly take. So you should think of this as like defining a new random variable. Okay, but what's the nice thing about, so in this sense, this Sn, if you notice, is the same Sn as that appeared in the statement of the central limit theorem. It's just that in the central limit theorem, you have to play a little bit more with it and kind of rescale it in a different way. But in this case, it's like kind of like a lot easier. It's just like add up the random variables and divide by n. So what's what's the nice thing about this sum of the random variables? Well, what is going to be the expected value of Sn is the expected value of x1 plus the expected value of x2 plus the expected value of xn over n. Okay, because the expected value is always linear, so you can just like break it into pieces. But because each of these random variables takes the same values with the same probabilities, they have the same expected values. So this is actually n times mu, where if you want, you can call mu the expected value of any of them. So mu here is like e of x1, which is the same as e of x2, which is the same as e of xn. Okay, and so these cancel out. So that means that these new random variable has the same average as the previous ones, as the ones that you started with. So Sn has the same as the xi. Okay, but what is happening with the variance? Now, what is the variance of the SNs? So let's put it here. Okay, so here is where you have to. This is where, like, again, more hypotheses are needed, or like all the hypotheses are needed. These, right, is the same as the variance of x1 plus x2 up to xn divided by n. Okay. I don't know if you remember this, but I mean, n in this case is just like a constant. When you rescale something by a constant, like the variance just gets squared. Like you can take out the constant out of the variance by squaring it. So here, because n appears in the denominator, it just gets squared. So this is like one of the properties of the rescaling. This is one of the properties of the variance on the rescaling, is that you just square the constant. Okay. So you end up with this, but what is this variance of the sum? Because random variables are independent, the variance acts. So here you have to use the independence. So this is going to be n times the variance. Let's call it sigma squared, because where sigma squared is going to be the variance of any of these, because again, all of these random variables have the same variances because they take the same values with the same probabilities. And so here you're dividing here by n squared. So here sigma squared is the variance of x1, which is the variance of x2, which is the variance of xn. So what do you end up with? This is more interesting. You end up with the fact that the variance of Sn is sigma squared over n. Is that making sense? Are there any questions about this up to now? But this is like a good place to remember what the variance was. So the variance was like the original definition of variance I had given you at the very beginning was the average or the expected value of the random variable minus its mean squared. So if you remember the original definition of the variance, it was this. It's just that in practice, how many times I computed it, it was like the second moment minus the first moment squared, but like this was the original definition of the variance. So this is well, how can you think about this formula? If you look at this ratio, right, and the numerator is fixed, so if you imagine kind of running the experiment many times, as n goes bigger, gets bigger and bigger, so as n goes to infinity, right? This is kind of what we're getting. So what this is saying is that kind of like as you add up more of these random variables, how much they add on average, they are closer and closer to this mean, to the the like how much they did. Like you can think of the variance as some sort of like deviation from the average, right? Because you're kind of computing like some sort of like error of how much the value of the random variable differs from this average. So what this is saying is that as n gets bigger, on average, the values of the sum deviate less and less from the from the expected value. So that's kind of nice because it's kind of saying that in a sense, like the SNs are concentrating around mu. So in a sense, like this is saying, so this suggests that the SNs that SN is concentrating concentrating about mu. And that's kind of what the law of large numbers says. So that, like, I still haven't said what the statement of the law of large numbers is, but what the law of large numbers says is the following. So here's the law of large numbers. It says like just fix your favorite constant epsilon positive. Usually, if you remember calculus, like you would use a letter epsilon whenever you think of a number as being really small. Although the law, I mean, the law of large numbers like allows you to choose any epsilon, but I mean, it is psychologically useful to think about it as being small. So what the law of large numbers says is that, let me see if we have it. Wait a minute. Yeah, is that the and use a hypothesis from earlier and with the hypothesis from before. What this is saying is that the limit as n goes to infinity of the probability that Sn minus mu is greater than epsilon, that is 0. So what does this say? Let's think about it, what it says. Like, so this is saying like, what does Sn minus mu in absolute value mean? That just, let's make it like with a diagram on the real line. So think of the values of Sn taken somewhere on the real line. Somewhere here is mu, and here's like the interval, mu plus epsilon, mu minus epsilon. So if Sn minus mu is bigger than epsilon in absolute value, that means that Sn minus mu, Sn is kind of outside. Let me write it here. If Sn minus mu is bigger than epsilon, then Sn is outside the interval that I just colored on the number line. Sn does not belong to this interval. So meaning that like Sn could be somewhere in here, for example. So it's kind of like computing the probability that like the value that the random variable happened to take was kind of outside at some distance epsilon from the average. Okay. And so what this is saying is that as n gets larger and larger, it can still happen that you will have like this average sum to be bigger than the distance larger than epsilon, but that will become more and more unlikely because this probability is going to 0. So what this is saying is that as Sn is getting really large, it is very unlikely that your average sum would be outside some interval of distance epsilon from the mean. And the thing is like, since epsilon could be arbitrary, that's kind of, I mean, you do have to fix the epsilon first, but this is saying it's like this statement is kind of true no matter which distance from the average you have chosen. So you fix your favorite distance from the average, that's kind of like your tolerance level for the error that you are willing to accept. And so within that bandwidth around the average, like, it is very unlikely that this average sum will kind of land outside of it. It can still happen, but the probability of that happening will get smaller and smaller. Is that making sense? Are there any questions about this? So these usually have something that's called the frequency interpretation. So the frequency interpretation is the following. Like, let me just do it in a simple case where like, for this interpretation, for this Bernoulli random variable. So imagine that x1, x2, up to xn, all of them are Bernoulli random variables. With parameter p. So again, that just means that the probability that xi equals like 1, or let's just call it like the probability, yeah, of getting 1 is p, and the probability that xi would be 0 is 1 minus p or q, right? And so here 1, you think about it as being a success, and 0 as a failure, right? So maybe you're doing an experiment and you only care about whether you got a specific outcome or not. So the outcomes, I mean, usually how I have described them is like whether you're getting like a head or a tails, but that's like a very, specific interpretation. Like you could say my out, maybe you just care, like for example, how would you say, you want to say what's the probability, like maybe you care about how often it rains in New Brunswick, right? So the success, like the success would be, if there's a day where it rained, you would count that as a success, right? So you would say that a rainy day is a success, and a non-rainy day would be failure. So, or and something, okay, almost anything you can kind of phrase in those terms, right? So you could also think about like, you know, you want to know how dangerous, like, like the side effects of a medicine, experimental drug that you're testing. So you could call, like, I mean, obviously you wouldn't want to call this a success, but you could call the success like, a bad reaction. So like success has like connotations, but you should ignore those connotations. Like, so success just means like that, like an outcome you're trying to measure occurred, right? So you're trying to measure like your bad reaction to like this experimental drug test. So that would count as a success. Um, in this like perverse way of looking at things. So you and then 0 would be no reaction whatsoever, right? So that would be a failure. So like almost many setups, if you just care about whether a specific outcome happened, right? Like have this flavor of being a Bernoulli random variable. And so in this case, x1, x1 plus xn would count, as we have discussed many times, the number of successes in n experiments, right? So in the example of the weather in New Brunswick, the experiments could be just like each day is like one experiment. So you do this, like if you do this 7 days for a week, and it's 7. If you did it for a month, and it's like 30, and so on. Okay. So x1 plus up to x1 plus 2, x2 plus blah 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 up to xn is like kind of the number of successes. And then what is what is x1 plus x2 um, up to xn divided by n? That would be the frequency you interpret that as a frequency, relative frequency of the successes among the total number of experiments. So it's kind of like how frequent the successes occurred in the n experiments. So like again, like here the frequency, like if you say like the frequency was like, maybe you like, like maybe there were like 3 rainy days in a month, right? So there were 3 successes in a month, which are 30 days. So the frequency would have been 3/30, which is 1/10, right? So here you would have said like that the frequency is 1/10. So the frequencies are actually, you can always think about them as ratios. So they are kind of always naturally between 0 and 1. So what the law of large numbers is saying is that the probability that let's call this frequency Fn because it depends on n, right? That the frequency of Fn minus mu, what is I don't know if you remember, what's the expected value for the Bernoulli random variable in terms of p? What was that? That one is easy.
Is it NP?
It's NP for the binomial one. It's just P for the Bernoulli one. Yes. So it is just P in this case. But if I had, right, because like this mu, what mu refers to here, in this context, mu just refers to the expected value of one of these single random variables. Otherwise, yeah, it would be NP. But yes, it is P here. And so what the law of large numbers says, in this case, is that the probability that the frequency will be like, like the law of large, oops, I should say this like as a limit, sorry. So limit of this. So what the law of large numbers says is that the probability that the frequencies that you're measuring differs from the from the like theoretical. You should think of this p as some sort of like theoretical probability, and this is like some sort of like experimental frequency, right? So this is like some sort of theoretical probability, and this is kind of like the frequencies are things that you can actually go and measure, like this. So it's kind of like some sort of experimental, it's like an experimental value. So what the law of large number says is that the difference between the experimental value of the frequencies and the theoretical value of the probabilities, that should get, if you're willing, if you accept a margin of error, right, then these frequencies can be outside, outside like your error of tolerance, but that will become more and more unlikely as n goes to infinity. So that kind of like that is why in many approaches to probability, like you kind of try to like there have been attempts in the past to define like probabilities in terms like of frequencies, and this is one of like the motivations behind it. It's I mean that runs into a bunch of problems, but it's not like based on that, on this idea of the law of large numbers, it's kind of like a reasonable thing to try to do. So, and this is what I mean, like in many, again, especially this is more common like in the natural sciences, where you can imagine that you are actually reproducing an experiment over and over multiple times. Many times how if you thought that you're making predictions about probabilities, the way you would try to verify those in practice is by actually running the experiment over and over, computing the frequencies, and just check whether those seem to be near the values for the probabilities that you had predicted. I mean, this is kind of how it's done in quantum mechanics, for example. You have like that is a good place because you can compute the probabilities theoretically, and then you can you can just check that whether the probabilities that you would predict from quantum mechanics match the probabilities that you in the laboratory. But like that, like when you say like the probability in the laboratory, you actually mean the frequencies. There's no, there's no device that can actually measure like probability is kind of weird. It's not like math or electric charge or other things. It's not something where you can just measure directly. So that's what makes it tricky. So like the best that you can kind of try to use as a proxy for probability in many contexts is just like this frequency stuff. So uh, that's why this is one of the reasons why probability can be a difficult topic if you actually try to understand what's going on. Um, Okay, but okay, this is kind of like, but like again, like the idea of these large numbers, it is plausible if you think about it. So, and the proof is for this weak version is actually very, very, very simple. So I'll tell you what the proof is in a second. But I thought I should just like give you the statement first, to give you like so that you like there would be some motivation for what I'm about to do. Is that okay? Are there any questions about this? Okay, so the proof all boils down to a very famous inequality, which is called the Chebyshev inequality. So the proof is really, really simple. So it's called the Chebyshev inequality. So let me call this, I don't want to, okay, I'll use the letter T, because I don't have like a many good, I don't want to use X or Sn because they're kind of already within some context. So let's call T a random variable. Why not? So T is going to be a random variable. And Chebyshev does the probability that T minus mu is less or equal to C is that's less or equal to sigma squared over C squared. That's all that it says. What is mu here? Mu is the expected value of T, and what is sigma squared? That's the variance of T. So again, it's kind of like saying, like again, if you do the picture, here's mu, you're giving yourself some margin C, which I'm calling C. So here's mu plus C and mu minus C. And so here, what I'm computing, what this probability refers to is a probability that T is somewhere outside this interval. Is that making sense? So P of T minus mu greater or equal to C means like the probability T is outside the interval. Whether it's open or closed, that doesn't matter too much. So I'm not worrying too much whether you think of the intervals being open or closed for our purposes. Okay. And what's the proof of that? Well, it's like the only thing that's a little bit odd about the proof. It's not too complicated, but it's not so clear how you would start with it. Because usually, like, when you try to prove like an inequality, you kind of start with the left-hand side, psychologically speaking, and try to get to the right-hand side. But for this inequality, it's kind of easier to start with the right-hand side and get to the left-hand side. So that is like the only tricky part there. But once you kind of realize that that's where you have to start, like it is like relatively straightforward. So like the proof is like you just have to write like the sigma squared, which was the variance of t squared. Sorry, the variance of t. You have to use it. Use the definition that I had given you earlier. I mean, or like a long time ago, right? Which is the expected value of t minus mu, and that's like the integral from minus infinity to infinity. Of you know, t minus mu squared times the density of t dt. Is that making sense? But then what happens here? This integral, right? This is like an integral that in principle is from minus infinity to infinity. But what you're integrating here is like you know, only positive, non-negative quantities, right? Like this is the square of a number, so this is always non-negative. The densities are always non-negative. So this integral for sure is going to be bigger or equal than doing the same integral over a smaller interval. So basically, I'm going to do it over the set. Over where? I'm going to do it over the integral from minus infinity. I'm going to do it over the region where this probability refers to. So I'm going to go from minus infinity to mu minus c. Plus the integral from mu plus c to infinity of t minus mu squared f of t dt. Is that making sense? So basically what I'm doing is like instead of doing the integral from minus infinity to infinity, I'm kind of skipping this interval where, like, you know, I know that the variable t is close to mu. So I'm kind of skipping the region where t is close to mu. Is that okay so far so good? So again, it's just like here, I'm just changing the region of integration by something smaller, right? So I'm skipping. So basically, I'm ignoring this interval I sub c. You can call this interval I sub c. So here, what I'm doing here is ignoring I sub c. And why do I want to do that? Because if I do that, then what happens here? What is t minus mu squared? Well, this is in the region. This is in the region. You're here in the region where the distance between this and this is bigger than c in absolute value. So t minus mu squared is actually bigger or equal to c squared. So this is actually, like, what I'm going to do is kind of replace, what I'm saying is that each of these is going to be greater or equal to c squared, each of these terms, because like you're choosing the domain of integration precisely in a region where t is more than a distance c from mu. So that happens. So each of these can be replaced by c squared. And the advantage of doing that is that you only keep the density function being integrated. Is that making sense? But then, but this is just a probability. I mean, once what does it mean to integrate a density function? That just like the integral of a density function is just like a probability, right? So this is like the probability that this is just a probability that the random variable is on this side here, and the other integral is a probability that the random variable is in here. So when you add them together, that's just a probability for the random variable to be outside this integral, this interval, which is like the same that I wrote as a probability that t minus mu in absolute value is greater or equal to c. So this is how you get c squared times the probability that t minus mu is greater or equal to c. Okay, so if you look at it, so what we found is that the sigma square is c is greater or equal to c squared times this probability. And now you just divide both sides by c squared and and then just like write the inequality in the different order. So is that making sense? And let me write, instead of sigma square, I will write the variance of t. That would be better. It would look better if you write it like this. So, and why is that useful? For our problem, let's just take t to be Sn and c to be epsilon. So what this is saying is that the probability that Sn minus mu is greater or equal to epsilon, which is what appeared in the statement of the law of large numbers. That's just the variance of Sn over c squared, but c squared just becomes epsilon squared. But since we had found before that the variance of Sn is 1 over n, that just gives you, well, sorry, the variance of Sn was, what did I write here? Was sigma square over, well, that's the variance of x over n. Let me write it like this. So the probability that Sn minus mu is less or equal to epsilon is less or equal to the variance of x over n epsilon squared. If you take limits on both sides of the inequality, then that's how you get that the limit is going to 0. Is that making sense? So that, I mean, it's kind of like interesting to go over the proof of the large numbers, but once you have the Chebyshev inequality, then you just have to put a couple of things together, but it's not too bad. But yeah, like the proof of the Chebyshev inequality does require this trick because it's not so obvious why you would have started with sigma squared and then kind of work out from there to the inequality of the probabilities. But yeah, this Chebyshev inequality is really, really useful for other problems in probability. So if you ever need to take more advanced courses in probability, I'm sure you will end up running into it again. Okay, so let me just so far so good. Any other questions about this? So let me just tell you quickly about the convolution. So like that's more or less the last topic that I wanted to cover officially for the course. So one is the next topic is the convolution. Okay. So what is the context here? Convolution of two random variables. I don't know if you saw the videos that are recommended by 3 Blue 1 Brown, but they're really useful. In case you haven't seen them, you should definitely watch them because they're very. He's especially very good with all the visual animations, so you should definitely check it out. It will give you a better insight of how the convolution looks like. So the idea of like the convolution is that you have x and y, two independent random variables. And you define a new random variable, which is z. Again, usually we'll call c, which is x plus y. And so the convolution problem, and this is actually related to this question, one of the problems I gave you on Gradescope for you to answer. It's just that on Gradescope, it was instead of x plus y, it was x times y or y divided by x, one of those. So I'm just doing the addition version of that. So the convolution problem is just to find the density function for f of c. So the question is just find. So the density of f of c in terms of like the densities of x and y. Like in fact, like this also works in the discrete case, but it's more interesting to do it in the continuous case because it's with integrals. So it's not that the same with the law of large numbers. There's like a Cheryshev inequality for discrete random variables. I did a proof that involves integral, but it's kind of like the same idea. It's not too different. You just have like maybe like a series or a finite sum, but you kind of approach it in the same way. Okay, and so how do you do that? Again, all these problems about finding densities, you have to begin with with what's called the distribution function, which is just a probability that the random variable is less or equal to a particular number. So you start with the probability that c is less or equal to a little c. Again, this notation can be confusing, but this, like when it's uppercase, it always means a random variable. When it's lowercase, it just means the values that it takes. So this is the probability that x plus y is less or equal to z. And this is great. Now this is like a double integral problem because if you plot, you know, you can plot the equality x plus y equals c, which is y equals z minus x. That's a straight line, right? Think of z as being fixed here. So it's a straight line with negative slope. If you think of z as being positive, it looks something like this. So the region that we're looking at, you know, like the region that we're looking at is should be something like this, if I'm not mistaken. Where did I write? Just give me a second. Yeah. So and then this is like what's this double integral? Is a integral like you can do it from minus infinity to infinity, from negative infinity to c minus x of I mean you can do it like with first you can put it in terms of the joint density function, but I'm going to do the independence assumption in a moment. So I'll change it as a product, but in principle at the beginning you can write it in terms of the joint density function. So that you see like this is like the correct formula in general. It's just that to simplify it a little bit, we will use the independence condition. Is that making sense? Are there any questions about this? So far, so good. So now if you use that independence, this is just the density of x times the density of y, dy dx. So you can pull out, I mean, doesn't matter too much for this at this moment, but you can write it this way if you want. You can take out you can take out the you can take out the first one out of the integration because the first integration is done with respect to y. And so you just get this integral. And so this is, I mean, again, like I'm doing a lot more like rewriting that is actually needed, but this probability from minus infinity, I mean, this density integrated from minus infinity to c minus x is just a probability that the random variable y is less or equal to, you know, c minus x. Dx. Okay. And so so let me just write it like, so the probability that x plus y is less or equal to z, or like, let's just write it with z, that's fine. I'll change it to x plus y in a second. It's just the minus the improper integral of f of x times p of y dx. Okay, but the density will be the derivative of this with respect to z. So the density is the derivative of this with respect to z. And the point is that it's a derivative with respect to z, so you kind of can move it inside the integral and just differentiate this because that's the only thing that depends on c. So if you do that, you'll find you get the integral from minus infinity to infinity of f sub xx times fy, but the point is that fy is now evaluated at c minus x by the fundamental theorem of calculus. Okay. So what this is saying, like, let me write it in a way that's more common. So what this is saying is that the density function for x plus y at some value z is the integral from minus infinity to infinity of fx, the density of x times the density of y, but the density of y is evaluated at this argument c minus x dx. Okay. And this formula, this particular integral, notice that this integral is not multiplying the functions at the same point, right? It's not taking the density at the value x. Oops. This is not taking the. This is, of course, this is like a product of functions, but it's a product of functions where the arguments are different values, right? So it's kind of like a shifted product in a sense, and this shifted product is like called like the convolution. So this is like a shifted multiplication, right? And this integral, all of this is called the convolution. The total, like the integral, this indefinite integral is called the convolution of fx and fy, which is sometimes written. Like this is a symbol for the convolution. Is that making sense? So again, like if you have, I'm sure like the majority probably you haven't seen the convolution before. So saying to you, oh, this is a convolution, I mean, it almost it's more like a definition. But if you take you know the again, if you take like a course where like you do like the Laplace transform or things like that, that convolution also appears there in you know in a natural context. So the but yeah. now it's just like a formula that we found, right? We found this formula. We found this formula, this particular version of the integral, we're just calling the convolution. Is that okay? Are there any questions about this? I'm about to do an example.
Notation question. Like in the bottom, you wrote like fx, then the convolution symbol, and it said fy like of z. I wasn't exactly
Yeah,
sure.
sorry. Yes, that's a good point. I will. What? Like, let me write it in a better way. This is like an asterisk. By the way, just like in terms of like symbols that I'm using.
I see.
Yeah. So it's just like you have two functions. In this case, they happen to be density functions, but you have two functions. Instead of saying I'm going to multiply them, right? Like usually, if there were no asterisks, you would just think of that as a multiplication, right? So this is kind of like a symbol to tell you, well, it is like a multiplication, but it's a little bit weird because before doing the product, right? Before doing the product, you kind of shift one of the arguments, right? So it's kind of like you're looking at the values of the functions, not at like the same position, but at like, one position is at x and the other is c minus x. So there's like a shift involved and then you multiply those. So the convolution, like it's kind of like a notation to try to remind you that it's like some sort of product, but not the ordinary product because it involves a shift and also like an integration, right? But that is like how would you like how you would do this? Okay. Is that making sense? So for example, like if you have seen the example of 3 blue 1 brown like videos, like he has like this cute case of like he has like a nice interpretation like of let's see, let me see if I can. Okay, like otherwise this would take me for an eternity, so okay, yeah. Let's say that you had like a weird die, with instead of having six sides, is like three sides. So triangular die, pyramid-like die. So let's talk about triangular die, which no one plays with, but it's just like it has because I don't want to do like a big table and lazy. So like, instead of having six sides, it just has three sides. 1, 2, 3, and let's say they're fair. So each side has probability 1/3 of, so each side has probability 1/3. Okay, so imagine that one random variable could represent like imagine that you have two of these triangular die. So you have like this is die 1, or let's call it die A, and Y is die B. So like the first one could land on 1, 2, 3. The second one could land on 1, 2, 3. So Z will represent like the sum of like you add up the faces on the die that you got. So like the sum of the values that you got, right? So let's try to there are a couple of ways you could think about this. Like let's say, just to make it more concrete, like let's say the first one is blue and the third one is red. Right, so the blue one could take values 1, 2, 3. And the red one could take values 1, 2, 3, right? So let's put here like the sums. So like the sums would be so I'm going to put in each entry like the sums that you got. So you got 2, you got 3, you have 4, right? Then you have 2, you have 4, and then you have 5, right? And then you have, okay, this, I'll do it. I'm doing it correctly, but I need a little bit more space. So it's like 2, 3, 4, right? Those are, again, I'm putting here like inside each entry, like the sum. So you have now 3, 4, 5, and then you have 4. You know, you have 4, and then you have 5, and then you have 6, right? So like the sums of these triangular dice, right? Like what are the values that the sum could take? The sum could take, so z, which is x plus y, can take values. What values can it take? It take values like 2, 3, 4, 5, right? 5 or 6. 2, 3, 4, 5, 6. Is that okay, everyone, with me up to this point? Because again, our die can only take 3 values up from 1 to 3. So those are like the probability. Those are the possible values, right? And then if you think of the, you know, if you think of the rolling of this die or whatever as being independent events, like the probabilities for each of these boxes is like 1/3 times 1/3 is 1/9. So this is 1/9. This is 1/9. Right? This is 1/9. This is 1/9. 1/9. 1/9. 1/9. 1/9. 1/9. Okay, but if you look, what is the cool thing? In fact, like that's kind of like maybe writing 1/9 everywhere is kind of like actually ugly. So I'll take it back. I mean, each of these like entries. Think of this as actually as a matrix. So each of the entries of this matrix has like a probability associated to them of 1/9. Now, for example, what is the probability that x plus y would be 4? That is, you know, that is how many times does 4 appear in this table? It just appears 3 times, right? Times 1/9, and thus 1/3, right? Is that okay is that okay? But how can you think? Okay, so the question is like, is there like an interesting geometric arrangement in which the 4s appear in this matrix? So if you look at this matrix, is there like a cute way in which the 4s appear? Do they appear completely random in the matrix or not?
They're all down like a diagonal.
Yeah, like, I mean, it's not the usual diagonal of the matrix, but yeah, they kind of are assembled along a diagonal, right? So instead, like one way in which you could have thought about this formula, instead of, let me write it as 1/9 plus 1/9 plus 1/9, which is the same, right? That's just 1/3. But one way to think about it is like you look at this diagonal where you got the 4, and then like you add up the probabilities for each of these boxes. Each box had probability 1/9, right? So what the convolution is doing in this case is it's kind of like, you know, it's kind of adding the entries of the box along the matrix, but like kind of like along a sheet, like some sort of like diagonal. And the same happens here, right? Like if you wanted the probability for a 3, you know, if you notice all the 3s appear, you know, all the 3s appear along one diagonal, which is cute. So this is like that. This diagonal, it's like a smaller diagonal, but so that means that's why the 3 is less common, and the 5s appear along some sort of diagonal, and the 2s and the 6s are too small, so they are their own diagonal, right? So, but it's kind of like, you know, if you think about it, like actually the sum is arranged in a very geometric way through like the constant values, right? That constant values happen along this diagonal. So when, you know, if you thought about the, you know, if you thought about it, you know, this is kind of like, oh, this is great because you know, let me just write it like here. Like, what is this entry? This is like, if you have seen matrix notation, this is what you would call the matrix, the entry 1, 3. This is the entry 2, 2, right? And this is the entry, what, 3, 1. So if you look, if you add up the numbers of the entries, right, along the blue diagonal, I plus j always equals 4, right? Along the blue diagonal, I plus j equals 4. So or j equals, you know, 4 minus I. So it's kind of like that's kind of the shift that you see happening in the formula for the convolution, because it is essentially like the discrete version of this formula where you shifted one of the indices. So it's kind of like this is kind of like I, and this is like C minus J. Is that making sense? So the same happens for the others, right? If you again, if you have seen the matrix notation, this is like for example, this is like 2, 3. And this is like 3, 2. And so in the green diagonal, 2 plus 3, I mean, like I plus j equals 5, right? So it's it's very like nice. I mean, if you like here, it is really looks really nice, everything. So, but so like the convolution, and again, like the discrete version of an integral is like a sum. So like it is like a sum of these like products of probabilities, but you do the shift. It looks even better if the die is not fair, because then this one happens like this side happens with probability p1, p2, p3, and this one with probability p1, p2, p3, and then you just see them. In fact, you could give like different probabilities to this one, like say two different unfair die. So this one is P1, P2, P3, and the other one Q1, Q2, Q3. And then you see that they multiply. You do see it a lot better if you don't make it fair. So that's like I mean, that is, but this kind of shows you that there's some sort of like shift happening with the sum, the integral or the sums. Is that making sense? And then let me see if I can show you this. I can have it somewhere in here. Is this one nice? Okay, this one is nice, but is this the one? Okay. Yeah. Yeah, and then like what happens in like these are kind of like difficult to represent visually because there's a lot of stuff, but if you look at the formula for the convolution, the thing is like for E you fix like a value for like here like in this animation I'm kind of like shifting one of them, okay? So imagine like this is what I'm calling Z in the formula for the convolution. So imagine you fix like a value for Z. So what does it like this does like you're kind of like shifting the graph, right? Like this is the effect of varying the value for Z or T. Because you were looking like T minus X or something like that. So that changes the shape of that it is essentially the same graph by translated. So imagine you choose like your favorite value, and then once you choose your favorite value, you do the entire integral, or you do the integral. So the integral is like an area under the curve, and so this gray area is the value of the convolution at this particular value of t. So it's kind of like it's a bit of it's a bit tricky because the convolution is an integral, so it's some sort of area. So at each value of t or z, the convolution is like the area under the curve. It's just that as you shift the parameter, then the value for the area changes. Okay. So I'll actually show you like the uniform in a second. But if you look at the uniform distribution, kind of like the area grows until both of them are perfectly aligned, and then it fades, like decreases. So there's like a sense like in which the area starts very small, and then once you match the graphs, like it reaches its peak, and then it starts shrinking again. And so you'll see that's why the convolution of two uniform distributions is like it is like a triangle. I'll show you that in a second. And then in this animation, you can do it with other things. So like if you do two Gaussians, like again, like the value for the area is the value of the convolution. So like the cute thing here is kind of like, I don't know if you see it, it's like you get like a baby Gaussian. So like the convolution of two Gaussians is a Gaussians. We also did that secretly. We already knew that with the moment generating stuff, because the sum of two Gaussians we have proven before it had to be a Gaussian. But like here you can, that's another way to see that using convolutions, and then you can play with the other ones. But I mean, it's kind of fun. But I'm just saying that it is a lot more like complicated to interpret, because like the value of the convolution function is an area, is an integral. So, but yeah, let me do that for the case of like the uniform distribution so that you see how it works. Yeah, is that okay? Are there any questions about this? So here's the example. Let me do it for, let's compute the convolution of two uniform distributions. So let's say so f of x is going to be the uniform distribution on 0, 1. So that means that f of x is going to be, it's going to be 1 if x is between 0 and 1, and 0 otherwise. So the uniform distribution on 0, 1 just looks like this. And and y is going to be the same. It would be like the uniform distribution. So it's like, again, it's 1 if 0 is less, if y is between 0 and 1, and 0 otherwise. So what this is saying is that you add up to random variables which have the uniform distribution. So it's like, imagine thinking, like concretely, you can think of it as like, you have the interval 0, 1, and you choose like a random 2 points from this interval, and you add them together. And no point on the interval, well, like all the points were kind of equally likely because you're using the uniform distribution. So it's kind of like 2 points at random that you add together, and the question is what's the distribution for the sum? What's the probabilities that you get for the sum? So it is similar to the case of the die. It's just that in the case of the die, it only took 3 outcomes with the uniform distribution. In this case, it's, it is taking outcomes over a continuous interval, but it's still with the uniform distribution. So again, the density for this one will be the convolution. So what is the density of y of c? It is the integral from minus infinity to infinity of f of x times f of y, what, c minus x dx. Is that making sense? So this is the one that's easiest. I mean, this is how you should start. I mean, that's like the formula. So that's like the place to begin. So far, so good. Now there is something that, I mean, like this integral looks from minus infinity to infinity, but there's like, immediately I can just change the bounds very quickly. So what's the first thing you could change the bounds for? Like, what's the easiest way to change these bounds to? It's not really from minus infinity to infinity, right? It's a lot less than that.
We just do
What
0 to
what's-
1. if
You could just
functions are
put
both
0 to 1. Perfect. Yeah, you can just put 0 to 1 because this is only non-zero from 0 to 1. So that's like the first thing that I'll use. And like between 0 and 1, this is actually just 1, the density, right? So it's just 1. So in fact, we're just integrating and so like you don't care about the 1 because it's so it's just you're integrating 0 to 1 of the density, the uniform distribution for C minus X dx. Okay. Is that making sense? And then what could you do? Let me let you kind of think about what you should do next. What could you do? How could you integrate this? How can you evaluate this function? Any ideas? Just think about it. Okay, so let's think about this. So X, what do we know about X? X is for sure between 0 and 1, right? I mean, you could do it in different ways. You could do it as a change of variables. What would be better? Well, let's do it with a change of variables. I think this may be easier to think about. So let's call y and z minus x. So the y equals minus the x. I was not thinking about doing it this way, but it could be better. So this would be f of y dy. And then what are the bounds of integration? When x equals 0, this goes from to z, right? And then when x equals 1, this actually goes to z minus 1. Okay, is that making sense? And like notice that c minus the upper bound is always smaller than the lower bound, so it makes sense to flip the integral to not work with this minus sign. Does this look better? I don't know. What do you think? And now, how, I don't know, this help. How would you integrate this function now? You have to, at some point, you will have to make cases on the values that C can take. Spoiler alert, right? But you have to be, well, the thing inside here, yes, but you have to be careful because you know, you do have to make cases on C. So let's think about what do I mean? Let's say that okay, for example, let's look at let's start with the lower bound, right? What happens if C, or okay, yeah, let's see. Yeah, let's break it into cases so that it's a little bit clear. So what happens if Z is less than 0, right? If Z is less than 0, this upper bound is going to be less than 0. I mean, this is even smaller, right? So what would you say the integral is? This one is easy.
Is it just 0?
It's just 0 because like these can only take non-zero values between 0 and 1, right? Sorry, this is non-zero only on 0 on the interval 0, 1. So if Z is less than 0, this integral, right? Let me, I can put it here if you want. Like here's the interval 0, 1, right? If Z is somewhere in here, right? Here's Z, here's Z minus 1, right? So this interval from Z to Z, from Z minus 1 to Z is never in the region of interest, right? Is that making sense? So the, like, f of Z should be just 0. Is that making sense? Now there's a complementary case, kind of like an analog of that, that guarantees this integral to be 0, which is Z greater than what?
Greater than 1.
Well, okay, let's say you have to be more careful. There, you have to actually use that. You'll see in a second why, because you have to look at both bounds. So,
Oh, would it be
the thing,
2? So that the bottom bound is
right?
also.
Yeah, exactly. So if you take C greater than 2, here you have 0, 1. Oops. One more time. Now, right, now C is greater than 2, then this one was good to go. But C minus 1, right, when you subtract 1 from C, now this is still greater than 1. So now you can put here like C minus 1, and here you can put C. So you're still outside you're kind of in the same safe zone where you know that the values are always 0. So the density, like, you know, the density would also be 0. And then you get to like the danger zone, which is when Z is between 0 and 2. But there, it does still make sense to split it from when Z is between 0 and 1. And because now you have to, like, that way you will control, you will know a little bit better where one of them is. So let's do now the case where when C is between 0 and 1. Okay, and so what's happening here with the integral? So the thing is like this is going to start a little, C minus 1 is going to start a little bit negative, right? C minus 1 is going to be a little bit negative, and somewhere in, like, you know, C would be somewhere in here, right? So the integral of the region of interest is from 0 to Z. Is that making sense? That's the only place where like the integral is non-zero. So when you look at the integral from C minus 1 to Z of f of y dy, that actually can be replaced for the integral from 0 to z of 1 dy, and that just gives you z. Is that making sense? So that's where you have to be careful. It's not just like, it's true the integrand is 1 or 0, but it is more tricky than that because you kind of have to check how the shift affects the bounds. Is that okay? So and then the last case is when z is between 1 and 2. Let's do it again. So you have 1, 0. Now z is z is now outside the interval of interest, but z minus 1 is a little bit inside. So now the region of interest goes from z minus 1 to 1. And this is what 2 minus z. Okay, so what did we find? We found that f of z of the density for the convolution is z for z between 0 and 1, 2 minus z for z between 1 and 2. And 0 otherwise. So how does the graph looks for this function? Well, it's kind of like a straight line until 1, and then it starts decreasing until 2, right? So it looks like a triangle. The graph, like the density, looks like a triangle, meaning that it is more likely to get, like, the peak is here. That's saying that it's more likely to, what's the value for the density there is just 1. What this is saying is that the region that's the sum where if you choose like two numbers at random from the unit interval, the most likely sum would be concentrated around one, because, like, kind of like half of your choices would be less than one half and the other half would be above one half. So on average, that kind of should concentrate around one half plus one half, which is 1. Is that making sense? So this is why sometimes this is called the triangular density function. Is that okay? Is that making sense? Is there any questions about this? Okay, so so this is officially everything that I wanted to cover for the course. As I said, the next 2 remaining days of class, I'll just do more like examples or things like that. And then the Wednesday is when we would have like the final exams. I'll send you like again like a study guide, more information about that between today and tomorrow. Maybe just to finish this up. I mean, this is more like a fun aside, but I think it's like an interesting thing to know. Um, okay, so let me do it like this. Let's say you have like XY plane. So on the XY plane, you have like the unit circle, right? And you also on the XY plane, you can also draw like the unit square center at the origin. So you can also draw the unit square center at the origin. So meaning that each side of the unit square you want it to be a 1. So this 1, 1, 1, 1, right? So for example, what is like so what is this vertex? This is a like each side, like half of the length of each side has to be the length of each side is split evenly on the positive and negative axis. So this is the point 1/2, right? So on the unit squared, one of the corners is 1/2. And what's the let's call this P, right? What's the distance of P to the origin? Well, that's just Pythagoras theorem, right? That's just the square root of 1 square or sorry, 1/2 square plus 1/2 squared, right? Which is 1/4 plus 1/4. So it's like the square root of 1/2. So like the distance that I'm computing right now is this distance, right? Which is less than 1, right? And so that's why this unit square would be inside the unit circle. Is that making sense? So that's what you would have there. So far, so good. Now, what is let's do this in 3 dimensions. So this is 2D. Here's in 3D. So you can have, what's the analog of the unit circle? The analog of the unit circle would be the unit sphere, right? Um, so you have here the unit sphere. And instead of like the unit square, right, you can talk about the unit cube. So you could have here like the unit cube. So again, it's centered at the origin. So each side is like, each side has length 1, but half of it is on the positive axis, half of it is on the negative axis. So what does that mean? It means what are the coordinates for this? Let's think about the same as before. What are the now you have one of the corners, one of the vertices, right? What's the coordinate for this vertex? Is it clear that it's 1/2, 1/2, 1/2? Is that making sense? Because you move 1/2 in along each side to reach the corner. So what's the distance of this point to the origin? Well, it's the square root of, I mean, it's you square each side, right? So it's 1/4 plus 1/4 plus 1/4. right? So that's the square root of 3/4, right? And that is that making sense? That's still a little bit less than 1, right? So the unit cube is contained inside the unit sphere. Is that making sense? So the unit cube is inside the unit sphere. Also, something I didn't say, right? What is the area of the unit cube? Sorry, what's the area of the unit square? Well, each side has length 1, so it's just 1, right? What's the area of the unit disk? Is pi r squared, but pi is r is 1, right? So the area of the unit disk is just 1, right? Now what's the volume of the unit cube? It's just 1 times 1 times 1, right? So it's 1 cubed, which is 1. What's the volume of the anyone remembers the volume of the unit sphere?
Is it 4/3 pi?
Right, it would be 4/3 pi r cubed, but it becomes 4/3 pi, right? And I don't know if you see what's going next. So I did it for 2D, I did it for 3D, right? So let's think about what happens in 4D. So what's the analog of that sphere? It's called the hypersphere. I don't have enough, I don't have like a good visualization for that. I would rather draw like XYZW, but I cannot really draw that, right? Because I have to draw the 4 perpendicular axes. But there's still like a unit hypersphere. Like which is x squared plus y squared plus c squared plus w squared equals 1. Okay, and that consists of all the points in 4 dimensions that have distance 1 to the origin. And then there's a unit cube hypercube center at the origin, right? And it still has a vertex, right? It will still have like a vertex, like similar to the P that I had drawn here or here. Okay. So what do you think the entry? It has to have 4 entries, and what are the entries for this vertex? It's still the unit cube center at the unit hypercube center at the origin, so it's 1/2, 1/2, 1/2, 1/2. Okay, and then what's the distance of this point to the origin?
Is it just gonna be 1 this time?
It's now going to be 1. Okay, good. So right. So it's going to be 1, right? Because it's 1/4 plus 1/4 plus 1/4 plus 1/4, right? So it barely touches, like, what does it's 1, as you were saying? So what does it mean? That it means that in 4 dimensions already the hypercube is touching, the corners of the hypercube touch the unit sphere, right? That's what this means. Like, I cannot draw this properly. Like, I don't know what to draw. Like that. I mean, you have to imagine that somehow like these vertices touch the unit sphere. Okay. And what do you think would happen next? What's and we can say something about what is um the volume in this case for the unit cube, the hypervolume, which you would call equals 1. And there's like a formula for the hypervolume of this hypersphere, but I'll write it in a second just to say something that will happen in a moment. So I'll write the formula for the volume in a second. But what do you think happens in n dimensions? So in n dimensions, so in n dimensions, you would have like the hypersphere, right? Like you kind of run out of names. In fact, let's just start just calling sphere, like. And you cannot keep using letters of the alphabet, right? So you just write x1 plus x1 squared plus x2 squared, blah, 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 plus xn squared. It consists of all the points in n-dimensional space that have distance 1 to the origin. And then you would have like a you can still talk about the unit hypercube. A center at the origin. And so you still have this point P, which is 1/2, 1/2, 1/2, blah, 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 up to 1/2, all of them of size like n entries, right? And so what's the distance of this point to the origin? It is like 1, you square each of, like the Pythagoras theorem still continues to work. So it's 1/4 plus 1/4, blah, 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 plus 1/4. So how many of them are there? There are like n of these 1/4. So you get root of n over 4, right? So here you see again that when n equals 4, you get 1. And so this is just square root of n over 2, right? So what is that saying to you? Like already once n is greater than 4, right? When n is greater than 4, the unit hypercube somehow is part of it is outside the unit hypersphere, which is kind of weird if you think about it. So like in 5 dimensions already, like the unit hypercube, like something, like sometimes like people say that in higher dimensions it looks like spiky, but it's still like, I don't know how that useful it is to say that it's spiky. It's not, there's just not like an obvious way to visualize that. So it's kind of like you have the unit hypercube, and then you have like this unit hypersphere, and like already in dimensions greater or equal to 4, the corners are kind of outside the sphere. And in fact, like as n gets larger, the corners are farther away from the sphere, right? From the unit hypersphere. So in fact, when you have a lot of dimensions, what happens is that you have like the sphere, and you kind of have this super stretched out unit hypercube, which now looks like something like completely crazy. And if like the interesting thing that happens is that the volume of these hypercubes, like it's always 1 times 1 times 1 times 1 times 1, so it's always 1 to the n. Well, yeah, I agree with you that that cannot be a cube, but I don't know how to represent it. There's really not like a good way to draw it. Just kind of looks, it just is like a good example of where your intuition kind of completely collapses. But what happens is that if you compute the volume of the hypersphere, I mean, there is a formula for it. Let's see if I should write it. Let's see. Yeah, well, I mean, I can. Like if you haven't seen it, like it is like not too illuminating. And you also have to talk about what's the a fraction of factorial, but that can be done. Like if you take like the point is that if you take n r equals 1 for the unit hypersphere, you get something like this. Sorry, n, I meant n here. You can, like, there's like a generalization of a factorial in the continuous case, which is called the gamma function that generalizes a factorial, so that you can talk about like, 3/4 factorial and things like that. The thing that is interesting that happens, like ignore the formula. The important thing is that that volume actually goes to zero and goes to infinity. So somehow, as n goes to infinity, this volume goes to zero. So as the dimensions start increasing, like the volume of the hypersphere starts shrinking to zero. So kind of like these cubes continue to have volume one, but that kind of all the volume is kind of spreading out of the hypercube. It's kind of escaping outside the hypercube. So all the overwhelming majority of the volume is kind of like near the corners of the hypercube, in fact. And so that's like the sphere somehow is becoming super thin. That actually has a lot of like consequences, like for data science or like statistical mechanics, because for example, what that like if you translate that, it just means that roughly all the energy, if you have like a system with particles, all the energy is kind of distributed evenly among the different particles. I mean, it's a long story, but it is not like it's more than an intellectual curiosity. Right, well, I mean, that is okay. It's right. It's also okay. That is less. You have to be careful because like there are these integrals, like Gabriel's horn, like which has like infinite air. What? How is it? Finite volume, but infinite surface area. So if it is possible for like the distance of the points to be further and further away from the origin and somehow still like everything integrate into one. I mean, it's like a simple integral, but it does look like, I mean, it just like means that somehow it's getting thinner, like right. That's why I'm saying it's very complicated to visualize. But it does, like it is one of these like what this means is that sometimes like you intuition with small dimensions should not be extrapolated to large dimensions. So there's a lot of like phenomena that happens just from the fact that you have like a large number of dimensions, which like in the case of like in our world, like the number of dimensions is 3. So the number of the analog of the number of dimensions here is kind of like the number of particles. So once you have like particles of the order, like, and your number of particles in your system is of the order of like the Avogadro number, which is 10 to the 23 or whatever, like kind of like this type of same rules start kicking in. And so that is what allows a lot of like the like usual statistical mechanics or probability arguments start working. But yeah, there are a couple like fun, if you go to YouTube, if you just click on enter like volumes or higher dimensional spheres, like just enter something like that and you'll find like a couple of fun videos like that tell you about like paradoxical things about these like these objects. But I'm just saying, just like if you haven't thought about this, like it's very easy to just like naively answer something and it would be completely wrong based on your intuitions. So sometimes like 2 and 3 dimensions can be useful for developing intuitions, but sometimes you can get to completely wrong results if you just like aren't careful enough. And they're just like things that happen once the numbers are like really, really big, that we don't have like a good sense. I mean, I honestly don't know how to visualize this. I just like, this is where like the algebra does have like a better like advantage over the geometry, because like when you look at the formulas, it does make sense. But when you look at you think about the cubes and the spheres as being so perfectly symmetrical and things like that, and once you kind of try to put that with how what this is saying, it's not so clear to square that circle. So I thought it's like an interesting thing to think about, but it does have like a lot of useful applications that we cannot get into. But I thought I should at least mention it, so that just to give you a sense that yeah, you have to be careful. Once you have large numbers, like many things can just behave completely different from like systems with small degrees of freedom, which is kind of what you would actually call this stuff. So like the analog, like in a gas, just to finish, like the reason why these spheres appear in statistical mechanics is that if you have like a gas, if you add the kinetic energies of the particles, and say, for example, that's some constant, like, or maybe not a constant, but that's a fixed value. The formula for the kinetic energy is like the sum of the mass, like the velocity squared. Like, well, you can write it this way. So you see, like the velocities of the particles are kind of working like you know, as this xi. So it is you know, you kind of have to find the volume of what's called like this is related to what's called the phase space of the system, but basically what you happen is that in phase space you have like a hypersphere, and then like you have to compute the volume of that to start computing like the quantities in statistical mechanics, because other but that's where like the sphere comes from like the formula for the kinetic energy, because the kinetic energy is literally just like the squaring of the velocity. So if you think of the velocities as like the xi, then that's like where the relation comes in. So it's like it's a fun. I mean, it is full of fun calculations actually, but yeah, it does require a little bit like it can be very tricky if you don't like, you know. But that's where like it comes from. But yeah, so I think it's a good place to end because it's almost 8. So as I said, like today we finish officially the course material. So like next classes, I will just try to do examples to ground this up a little bit more, like more things. But there are no more topics, so I'll just like write like the study guide and send it to you. And let's hope by tomorrow. I think that sounds good.
Have a good one, Professor.
Okay, yeah, you too. Bye bye.
Thank you, Professor. Have a good one.
Bye bye. You too.